you can see this is not the same. This is the exact answer, or 20, I'll do 21 as a third, 21 a third. I've got an answer that is ever so slightly out. Because, think about drawing this and then joining all these points up with trapezium. What's going to happen is you're going to get a little bit extra in each of those sections because the curve is going outwards like so. It's a concave curve. So when I join up points, I'm just getting, I don't know if you can see on the camera, I'm just getting a little bit extra each time. And as I keep on going up, I'm getting ever so slightly more and more just with these straight lines. And that little bit extra from 0 to 4 equates to 2/3 worth of extra. Likewise, if the curve went something like this, as I join up all my points, let's say I went like along like here, and like here, so on and so forth, you can see I'm actually getting less. These trapezia would not equate to the whole extra bit of the curve, and bits missed out. So depending on the shape of the curve, depends on if you get extra or less than the actual thing. Now, interestingly, if I put this into my calculator would actually give the right answer using the integration function. But for the most part, if you have a calculator method that involves square roots, then your calculator is going to deliver a very similar answer to what the trapezium rule gives you. Your calculator uses a very similar function to the trapezium rule. It's not quite the same, but it doesn't do the numerical integration. Okay, so that's one basic example of how the trapezium rule works. And it's basically just a use of the formula. Sometimes you might need to give a percentage change or a percentage difference depending on what you've actually ended up with or what your error is. And you do that from finding the difference from the actual answer. Like I've got there, I had 21 and a third. If I took away the 22, I can see that I've got 2/3 out from the real thing. If I divided that by the true answer, 21 and a third, that would give me a percentage out, the percentage that I am out of the original. Okay. So let's do one more example, the example from the book. Okay. This example involves doing the trapezium rule twice over. So first of all, we've got an example here. It says, use the trapezium rule to estimate the area of the curve of equations y is equal to root 2x plus 3 between the lines x equals 0 and x is equal to 2. And the first thing it says, use the trapezium rule with 4 strips. Okay? What that means is that n is equal to 4. If I imagine the shape of that curve, I'm splitting up into 4 different bits, which means when I do my little table, when you will always draw this table, or the table will be given for you, I'm going to go from x equals 0 up to 2, but I want enough to have 4 strips. And what that means for us is that I need to have 1 strip between these two, 1 strip between these two, 1 strip between these two, 1 strip between these two. I need 3 extra values in between. So in other words, I'm going to need to go up by a half each time. So 0.5, 1, 1.5. Now, plugging these in, and it's fine if you want to give them to 3 significant figures as you go, because otherwise you end up with very, very long numbers here. But if I plug 0 in, I'm going to have 0 times by 2, which is 0, plus 3. I'm going to have the square root of 3. Now I'm going to do all these in terms of exact answers to save notation here. Okay? 0.5 times 2, I've got 1, plus 3 is 4, the square root of 4 is 1. Okay? Sorry, the square root of 4 is 2. What am I about? Square root of 4 is 2. When I plug it in as 1, 2 plus 3 is 5. So I've got the square root of 5 there. 1.5, 2 times 1.5 is 3, plus 3 is 6. I'm going to put the square root of 6 there. And when it's 2, 2 times 2 is 4, plus 3 is 7. I've got the square root of 7. Okay, so that's easier to write out than decimals. Now you'll see in the notes, if you look at the example in the book, they write it out to 3 significant figures. I'm going to leave it as exact answers until the very end, just to make sure that I don't make stupid mistakes or round too soon, that sort of problem. So, this means the integral of y dx from 0 to 2 is going to be approximately equal to a half, as before, times by the height. The height between these, we've already worked out, it's the difference between each one of these. The difference is 0.5, or a half. Okay? So the half times a half times by. My y0 is root 3, plus 2 loads of y1, 2, plus y2, which is root 5, plus y3, which is root 6, close brackets, plus root 7, which is my yn. Okay? Now simplifying this, half times a half, I've got a quarter. And then if I start working out all of these bits, this is something I would do on my calculator. So I'd start working out that in the middle. I'd have my 2 plus root 5 plus root 6, making sure that on your calculator you actually press across one so that you get this as you go. Now that's already given me decimals. Times that by 2, then add it to root 3, then add it to root 7. And you end up with 17.74 blah blah blah. I'm not going to write, I will write it all down. That now needs to be divided by 4, because that's actually what I've got on the outside, and you will get 4.437,22939. 4.437,22939 units squared because it's an area, and then for three single figures, 4.44 units squared 3SF. So there you go, we've got the estimation. Now that is not the actual answer. That's an important point. This is an estimation. Now in part B of this, you've got to do the exact same thing, but we don't want 4 strips, we want 8 strips. Okay, it says using 8 strips, so that means that you're going to use the value the same, but you're going to have n is equal to 8. The only way this is going to change things is, instead of going across as the table did before, I need enough values such that I can split this function into 8 individual strips. So I'm going to go from 0, still going all the way up to 2, but instead of having 4 strips, I want 8 strips, which means I need to do my 2 taken by 0 divided by 8. That's going to tell me how much I'm going to go up by each time. Now, as it happens, I'm going to go up by 0.25. So 0.25, 0.5, 0.75, 1, 1.25, space already, 1.25, 1.5, 1.75, 2. Okay, and now I've got enough space to record all of these. So again, I would go through now, look at what we've done before. I've already got a few of these. Root 3, 2, root 5, root 6, root 7. You'd fill in the gaps. So 0.25 times by 2 plus 3, all of that jazz, and you would fill in what you can have for other things. So typing those in, so let's say I've got the square root of, this time I'm going to have 3 plus 2 times 0.25, just to make sure I get a nice simple form. This is root 14 over 2, okay? Or I write that, no, I'll write it as root 14 over 2. If I put in 0.75, I get 3 root 2 over 2. If I put 1.25, then I end up with root 22 over 2, or root 88. And last but not least, if I put in 1.75, I end up with root 26 over 2. So, the last bit now is to work out the approximation from 0 to 2 y dx is approximately equal to, again, a half times by the height. The height this time is how much I'm going up by. I'm going up by 0.25, so it's a quarter. Times by each of these adds up individually. I'm going to have my root 3 plus 2 times all of these individual bits here added up. So root 14 over 2 plus 2 plus root 3 root 2 over 2 plus root 5 plus root 22 over 8 plus root 6 plus root 26 over 2, close brackets, and then last but not least plus the root 7, close your big brackets. Typing all of this into your calculator will give you a final solution. The final solution will become 4.44 025. Okay, or again 4.44 to 3SF. And then we've still got our units squared, because then we are still dealing with area regardless of all this. Okay, units squared, 3SF. And there we have it. Interestingly, both of these answers were the same to 3 significant figures. That means that this is true. So 3 significant figures, this must be correct. Now, what's interesting is the different answers come later on. The reason for that is because this is going to be a more accurate form. The more strips you take, the more accurate the answer will be. So you need to take that into account when you are doing these sorts of questions. So it is unusual to get as many as this on a question in the exam, but it could happen. They're more commonly going to give you maybe between 4 and 6. The way the questions often look is that they will have a table drawn for you. Say, for example, they'll have the function and they will say, first of all, complete the table. So it might be, for example, y is equal to x plus 3, you're going to have x, you're going to have y, and they're going to give you 0, 1, 2, 3, 4, for example. You've got to fill in the gaps. There might be a few of them filled in already, but you fill the remaining ones in. Once you've done that, it will give you a state that you can then use the trapezium rule. It might then say in part B, use the trapezium rule to calculate an estimate for the area onto the curve. And then your final bit might be work out the actual answer by integrating this as normal. We can't integrate this just yet. We haven't learned how to do root 2x plus 3 differentiated. Okay, but we will do next year. But if they gave you something that you did know how to differentiate to integrate, then you could do that as well, and then you could work out your percentage error, for example, by working out how different it is from where you started, or where the real answer is, and then dividing through and times it by 100. Okay, so if you have a look in the notes, there's a bit more detail on each of those processes that we've just done. There is also a little bit more on how the formula comes about if you're unsure about my explanation at the start. After that, there's a little bit about the sketch, and you can see why it is an underestimate in this case. That's a little bit about what I was talking about, how if it's a, if as you're going through, if you've got a concave situation where the curve is bending inwards, as you join up your trapezia, you're always going to end up with a little bit less. But if it's a convex case, where if it's like this, you're actually going to end up with a little bit more each time. As you join up all your trapezia, you're going to end up with a little bit more. Okay, you've got to be aware of that as well. Like, is this an underestimate or overestimate? You can word it using that. Looking at exercise 8F. Okay, 8F gives you, as I said, some tables, and those tables have gaps in. First of all, you have to complete the tables. That will be 1 or 2 marks at the start of the question. Once you've completed the tables, you use the trapezium rule. The trapezium rule is given on page 167, but it is also in your formula books each time. So you would complete the formula, you can use the trapezium rule.